So last week, we start to talk about the mass balance with chemical reaction and then how, but before we really do the mass balances, we need to know something, the basic knowledge about the reaction. So these are the four terms you really need to know and you really need to remember. Last week we talked about limited reactant, right? So according to this equation, which will be the possible limited reactant in this reaction? Do you know that? I need I need you to find out what is limited, which one is the limited reactant in this reaction, and which one is the excess reactant in this reaction. And you also need to know the fractional conversion, the definition of the fractional conversion. What is this? And also you need to know the extent of reaction, the degree of the reaction. So we all have this the definition. So you need to remember all of this. Today we want to talk about uh, the multiple reactions. You know, multiple reaction is somehow is a little bit complicated compared to the single reaction, because you know, if you have more reactions, that means the that you will produce more chemicals. So in terms of multiple reaction, there are another two terms you need to remember, or you need to realize. One is called yield, one is called selectivity. So let's have a quick understanding about the multiple reactions. The multiple reactions is that normally you will have a desired reaction, okay, the one you want, and others are all called side reactions. Side reaction is that you don't like the products. So here is the example. The example, for example, this is the one of the example that C2H6. After cracking of the C2H6, you produce C2H4 together with hydrogen. And this kind of process we call dehydrogenation process. As you know that this C2H6 take out one molecule of the hydrogen, so it becomes C2H4. Okay, this is desired reaction. However, unfortunately, H2 hydrogen will have chemical reactions with the reactants C2H6 and produce methane CH4. And we don't like CH4 in this process. So this is what we call side reaction. Side reaction. So that means that the product will have chemical reactions with reactants. And this is what we call side reaction. And unfortunately, again, the methane, when you produce from the side, the products produced from the side reaction will, will produce again, because the C2H4 will also have chemical reactions with C2H6. So you will produce CH4 again together with C3H6. So it makes the chemical reaction more complicated. Okay, so in this case, you have one input, which is C2H6. But how many outputs you will have? 1, 2, 3, 4, even 5. If you don't have complete reaction, right? So normally you will have 4 to 5 species in the output stream. So this is what we know about the multiple reactions. So what's the definition of the yield? So these are the 3 chemical reactions we just introduced you in the previous slide. So the definition of the yield is that the moles of the desired products formed. This is what we want, right? This is what we want. And the moles is the number here. You want to put a number here. Divided by what? Divided by the moles that would have been formed if there were no side reactions and the limited reactants had react completely. What does this mean? It means that assume there's no reaction. You remove these two, there's no reaction. And this one react completely. There's no C2H4 anymore because the limited reactant has react completely. This is limited reactant because here is only one chemical, right? So you need to know the definition that mean. So you need to, in order to know yield, first of all, you need to know the definition. So the moles of the desired product form means that with the side reaction, what's the real C2H4 form? You will put it in on the top. In the bottom is that assume there is an ideal case, no side reaction, and then reactant react completely. And this is the number. You put a number here. For example, if this have 1 mole C2H6, and you will produce 1 mole of C2H4, ideally, right? Okay. So here is an example. For example, you in the reality with the side reaction, you might probably produce 40 moles of the C2H4. And then if we allow these two chemical reaction, and then you can produce 15 moles, ideally, C2H4. So you can say 40 divided by 50. That will be 80%, right? 0.8. So this is the definition of the yield. And how about selectivity? Selectivity means that how selective is this amount. So assume we have 1 input and we have 4 to 5 output species, right? So the definition of selectivity is the moles of the desired products form. So compared to the previous slide, this will be 40, right? Exactly the same, the moles of the desired product form. And then what's divided by what? Divided by the moles of the undesired product form, which is, this is the product, right? This product, H2CH4, and then C3H6. So you have these three species, the amount of these 3 species. So so you might have some example like this. So I want you to remember the definition of the yield and the selectivity. Okay? So I'm going to give you some examples here. So for the yield and selectivity, this is an example of a C2H6, and you have definition here, right? So if you want to write down a flow chart, then how can you write down the flow chart? Okay, this is a reactor, right? Oh, you have 1 input, which is C2H6. Okay? And then assume, in this case, assume C2H6 is reacted completely. Of course, you only have 1 reactant, and obviously you understand this is a limited reactant. And if C2H6 react completely, then you only have 4 species come out. The first one will be the main products, which is the one we want, C2H4. And other 3 are formed by side reactions. They are CH4, C3H6, and H2. So you have 1 input and 4 outputs. Okay? So this is how you draw as a flow chart. So what happened to the yield? Yield is what? As we know, that's the moles of C2H4, which is formed. And divided by what? The moles of C2H4 expected if there's no side reaction. Okay. And how about selectivity? If you know the selectivity definition of selectivity, that will be moles of the C2H4 divided by what? The moles of the CH4 plus H2 and the C3H6. So please remember the definition, and it is important. Okay, so for the mass balances in the multiple reactions, is that, you know, last week we learned for single reactions, we understand the moles of the final products equal to the moles of the initial mass or moles plus what? Nu times Xc. Nu is what? Stoichiometric coefficient. Remember this stoichiometric coefficient. If this is a product, Nu will be positive. If this is the reactant, Nu will be negative. Negative. Okay, Xc is what? Extent of reaction. You know, different reaction, you have different extent of reaction, different numbers, the degree of the reaction. Okay, so for single reaction, for this chemical reaction here, you can write down the moles of the C2H6 equal to the final moles of the C2H6 will be equal to the initial moles of the C2H6 plus Nu times Xc. How about multiple reactions? Multiple reactions, okay, here is the definition showing you here. Okay, how about the multiple reactions? Multiple reactions is easy because you just have n initial moles of the C2H6 equal, final, the moles of the final reactants of the C2H6 equal to the initial moles of the C2H6 plus what? The summation of the Nu times Xc. What does that mean, summation? Because if you have three chemical reactions, you need to do the summation of the H2, right? You need to do the summation of CH4 here. And you need to do the summation of the three equations of the C2H6 from these three equations. Right? So that's why you need summation. Okay? So you have final initial times summation of Nu times Xc. Okay? So when you do the analysis using mass balances, this is one. So here I'm going to give you an example. I make it easier for you. We in the previous slide we have three equations. Now let's make it into two. There are two equations. Here, of course, you understand this is the main reaction, and this is the product we want, and this is a side reaction. Side reaction. Okay. So this is reaction one. We have different extent of reaction. We call this Xe1. And this will be half Xe1. This will be 1 Xe1, right? Okay. And then how about reaction 2? We will have different Xe1 here. We call it Xe2. Xe2. If this is Xe2, then this will be 3 Xe2, right? And of course, you know this is a minus because Nu here is stoichiometric coefficient for the reactant. This will be the sign of the negative sign. And this 2Xe2 and this 2Xe2. So in order to make this possible, make this equation possible, you have final equal to initial times plus Nu times summation of the Nu times Xc. So how can we do this? How can we use this equation to make this example? So for the input, if we have input, that means NC2H4 bracket O is this one, right? Initial. And then this is initial. Okay? It can be 0. Okay, it can be 0 here. And you have reactions, which is 1 plus 2, right? So you have what? Here you will have Xc1 times Xc2. Here you will have half Xc1 plus 3 Xc2. And you will have Xc1 here. And you will have Xc2 Xc2 here and 2 Xc2 here. And what is this? This is a summation nu times Xc, right? Summation. Xc1 plus X2 will be summation of nu times Xc for these two reactions, right? Okay. So as a result, you have output. So we know that output equal to input plus summation nu times Xc. So how can we write down here for this C2H4? Output, right? Output will equal to what? Input plus summation nu times Xc. And we understand this is negative because this is reactant, so it should be negative sign. Right? So this is exactly output equal to input plus summation nu times Xc here. Okay? This is the example of C2H4. And let's take a look of another case which carbon dioxide CO2. CO2 will be final, right? Equal to initial times plus summation to Xc2, right? So this will be the case of the carbon dioxide. Okay, you can make a case of this oxygen, or you can make a case of the C2H4O or H2O, as you like. So I just want to let you know that for the multiple chemical reactions, the mass balance will become final equal to initial plus summation nu times Xc. Okay. So let's take a look of the example 4.6-3. This is easy. So please read the text with me, and then after we read the text, let's draw the flow chart. So in the page 117, the reactions, there are two reactions, right? As you can see here, C2H6 becomes C2H4 plus hydrogen, and then C2H6 plus hydrogen become 2CH4. Taking the continuous reactors at steady state. Continuous reactor at steady state, that means there's no accumulation, right? Okay, the feed contains 85 more percent SM, and then balance inner. So obviously this reaction has inner gas. Inner gas means what? There's no chemical reaction. Okay, the fractional conversion of the SN is 0.501. So you know the fractional conversion of SN C2H6 is about 50%. Right? So this is what we call specification. Right? And first of all, you need to know what is the definition of the fractional conversion. Okay? And then the fractional yield of ethylene is 0.7471. Another specification, which is the fractional yield. So you need to know the definition of a yield, right? So we have two specifications. And then after that, calculate the molar composition of the product's gas and the selectivity of the ethylene to methane product. So you want to know, we want to distinguish what's the selectivity of the C2H4 and the CH4. Right. So, so let's start to solve this problem first by drawing the flow chart. So first of all, this is the chemical reaction. First one, C2H. Please take a look of this slide with me. So C2H6 becomes C2H4 plus hydrogen. So this is what we call Xe1, right? Because we don't know the extent of reaction. What's the degree of the reaction? Okay, the second one is C, and hydrogen will have chemical reaction is C2H6. So C2H6 plus hydrogen become 2CH4. And you have a chemical reaction, we call it Xe2. So how can we do this in the to draw a flow chart? So first of all, we have 85% of C2H6. Of course, obviously, balanced with what? Inner gas. So since you dilute the C2H6 in the chamber, you don't want to have a 100% of the C2H6 because the high concentration might cause dangers. Okay? Okay, we have 100 moles bases. Let's draw 100 mole bases, although they didn't tell you. So this is the basis. Right, and then we have two specifications. So as we know that we have N1, which is C2H6, this is unknown. And we have N2, which is C2H4, unknown. This is desired product, right? Desired product. And N3, which is CH4. And we also will have what? Remember here, you have inner gas. And you have N4 here. N4 is, sorry, you have hydrogen, N4. And you have another one, N5, inner gas. So you have two inputs, C2H6 and inner gas. You have 5 outputs, which are noted as N1, N2, N3, N4, and N5. Okay? So, with this flow chart and two specifications, can you get these 5 numbers? Can you? Of course, you think, well, Professor, you told me that before the midterm exam, you told me we better do the DOF first, degree of freedom analysis first. That's right. That's right. That's what I'm going to show you today or next or Wednesday. But before that, before we do DOF, let's do this first. Let's do a calculation first, okay? So basis is fit is about what is 100 mole, and you draw the flow, and you know that you need to write down the extent of reaction, which is Xe1 and Xe2. Remember this, okay? So you have balances input. You want to use the mass balance, which is input equal to output, output equal to input plus summation nu times Xe. You had so far you just know how to do the mass balance using this tool, right? Output equal to input plus summation nu times Xe. And now the problem is you have 2 unknowns here, Xe1 and Xe2. So in the total you have 7 unknowns. Okay, so for the C2H6, let's roll down that output equal to input plus summation nu times X. That will be N1. That's output, right? Output here equal to input. Input is 100 mole. And there are 85% of the C2H6 in the 100 mole. That means what? 100 times 0.85. And you need to plus what? Summation times nu times Xe. So you have Xe1, which is 1 mole here, and you have Xe2, which is 1 mole here. So what can you write down? The summation of Xe1 plus Xe2 with a minus sign in the front. So you have minus Xe1 minus Xe2 here. So N1 equal to this. Right? So you can write down N2, N3, N4, and N5. So this is CH4, which is N2. So N2 equal to what? N2 equal to input 0, right? N2 CH4 equal to initial moles of the C2H4, which is 0. And then plus what? The equation 1 has an Xe, so Xe1, and there's no C2H4 in the equation 2, reaction 2. So you plus 0. And because this is product, so nu, the sign of the nu will be positive, will be plus, right? Positive. So N2 equal to what? Xe1. Or you can write down CH4, you can write down H2, and you can write down inner gas. So obviously, in order to solve N1 to N5, you need to understand Xe1 and Xe2 in order to solve the problem, right? So N5, there's no problem because this is not involve chemical reaction. So you know N5 exactly will be the 15 mole. So now you got a key point. The key point is using the specification to get the answer of the Xe1 and Xe2 so that you can get the unknown of the N1, N2, N3, and N4. Okay? So how can we get Xe1 and Xe2? Remember that we have two specifications. The first specification is the fractional conversion of ethane, which is 0.501. So if you know the definition of the fractional conversion, write down here and equal to 0.501. Then probably you have chance to get the Xe1 and Xe2. Right? So this is mole reactive divided by mole fat. So the mole of the reaction of the ethane is what? So the mole of the fat will be initial, right? Initial will be 85. And mole react will be what? Will be this one, right? Will be this one. X minus Xe1 minus Xe2. Of course, we understand we need to have a absolute volume for this Xe1 and Xe2. So this is equation 1. So now you realize that I have two unknowns and I have two specifications. So I can get two unknowns, which are Xe1 and Xe2. Okay, so equation 1, you got this. How about equation 2? It's the fractional yield of the ethylene, which is 0.471. So as long as you know the definition, you just put a number in, or you just put the unknown into this equation. So the moles of the desired product form will be what? Moles of the desired product form, which is this one, desired form, which is what? Xe1, right? Xe1. And the moles of that would be formed, which is 85, ideally, right? 85. So this is the equation, Xe1 divided by 85 equal to 0.471. So bingo, you have two equations. You have two unknowns, two equations. You can solve the unknowns, which are Xe1 and Xe2. So once you know the Xe1 and Xe2, and I'm sure you know the N1, N2, N3, N4. Okay, so the key point in this example is as long as you know the definition of the yield and the selectivity. Right? Sorry, as long as you know the yield and the conversion fractional conversion. And now the question asks you to get selectivity, right? Right, so what's the selectivity? So once you have xe1 and xe2, and you put this xe1 to xe2, you got all the numbers from n1 to n5. And now you want to know the selectivity. Selectivity from the C2H4 to what? CH4. So C2H4 divided by CH4. And you know that will be N2 divided by N3. And you know Xe1 and Xe2, of course, obviously you understand, and you can realize the N2 and N3. Okay, so that's the this section 4.6, balances on reactive system. Okay, so let me summarize this 4.6. First of all, you need to know the stoichiometry, right? You need to know stoichiometric equation, stoichiometric coefficient, right? And stoichiometric ratio. And then you need to know limited and excess reactant. And you need to know the fractional conversion, the definition of fractional conversion. And you need to know the definition of eternal reaction. And after that, we introduce you chemical equilibrium, which there are two terms you need to remember well. The first one is called thermodynamics. The second one is chemical kinetics. So does anybody tell me which one is related with time? A, thermodynamics, or B, chemical kinetics? Which one is related with time? Raise your hand, 0.5 point. If you don't have good score in your midterm exam. There are about 12 students. Your score is less than 50 points. So you are going to have trouble. So if you don't want to have trouble once the term finish, you better get points as much as you can, right? Okay, tell me which one is related with time. First, chemical thermodynamics. A, B, chemical kinetics. Raise your hand. Yes. Which one is related with time? Thermodynamics. I'm sorry. It's wrong. Okay. Which one is? Obviously, do you know the answer, right? Why don't you raise your hand? I want to give you 0.5. Raise your hand. Which one is related? Yes. B, right? Good job. Chemical kinetics is something to do with time. Thermodynamics, thermodynamics is related to the initial stage, initial condition, and the final condition only. It's nothing to do with something in between. So once you get a book of thermodynamics, there's no time related equations in this book. Okay? But when you have the books of chemical kinetics, when you open the book, it's something always to do with time. Okay? Good. Right, so we are talking about chemical equilibriums. They are thermodynamics and chemical kinetics. Multiple reactions, you know that the final, again, I want to remind you that the mass in the final stage will be equal to the mass or the moles of the initial stage plus summation num times xc. Okay, and multiple reactions, you need to know two terms, yield and selectivity. So here is the four formulas or equations I want you to remember. So let's move to the section 4.7. Now we are really going to tell you how to do DOF and how to do the mass balances using external reaction or using molecular species balance or using atomic species balance. Okay? Right. So, when we do the mass balances on non-reactive processes, that's very easy because input equal to output. However, for the chemical reaction, you don't have probably the species created in the products, so you don't have input. So how can you do the mass balance? Using molecular species. So now we think of using atomic species balance. That might be another way to do it. So actually, in the section 4.7, we are going to introduce you 3 methods to do the balances on chemical reaction related to chemical reaction. The first one is extent of reaction. As we already learned in the section 4.6, because the final moles equal to the initial mole plus summation nu times x. This is the equation you need to remember, and this is what we do for the mass balances using extent of reaction. And then we also need, if you want to draw the flow chart, and there are 2 ways. The first is molecular species balance, and another way is atomic species balance. For the extent of reaction, you don't need to draw flow charts because you have an equation. Okay. So for a steady state continuous process, I think we don't have time to read, but I just want to tell you that if we have 100 kilomoles per minute C2H6, and we have output of 40 kilomoles per minute of H2. So we can write down something like this. As you know, this is what we call the hydrogenation process. You lose 1 hydrogen, so this is what we call the hydrogenation process. So you have input, which is 100 mole, and you produce 40 moles. In the beginning you have 0, and once you do the reaction, you produce 40 moles of the hydrogen. Obviously, you understand, because this equation is stoichiometric coefficient is 1:1 for the CH4 to H2. So obviously, you understand you produce 40 kilomoles per minute of the C2H4, right? So how many moles of the C2H6 will be consumed? 40, right? 40. And with a sign of minus in the front. And then in the end, for the output, we understand you have 60 in the end, and you have 40 and 40. This is easy. Junior high school level, right? Right. So if we want to do the internal reaction, and we want to make it become flow chart, we don't want to write down something like this. And then that will be, if we have reactor here, which is 100 kilomoles of C2H4 per minute into this reactor, we have a stream, we have a bar here, we have a stream going to the reactor, and the output stream will contain what? 40 kilomoles of hydrogen. And then we don't know, because this is known, right? This is known, right? 40. And there's one thing we don't know. You see the output, the mole of the C2H6 in the output stream, which is N1. And N2 is the C2H4, N2. This is what we don't know. Okay? So how can we use this flow chart to solve the problem using molecular species balance or atomic species balance? So for the molecular species balance, we need to know that input plus generation equal to output plus consumption plus accumulation. So as we know, this is a steady state process. So we will remove accumulation terms away from this general balance equation. Why? Because it's steady state. So there's no accumulation. If there's accumulation, then this process will be unsteady state. So basically, we have basis in 100 kilomole, right? So for the general balance equation, you have 4 terms: input, generation, output, and consumption. In comparison to the non-reactive species, only have 2 terms: input equal to output, right? So this will be, you have generation term and consumption term here. So we draw the flow chart as we write down the flow chart like this. So basis is 100 kilomole per minute, and then flow chart, we draw the flow chart. And next will be the DOF, degree of freedom analysis. We are going to introduce you this data, but let's find out how to do the calculation first. What's the calculation? So according to this equation, for the C2H6 balances will be input equal to what? Output plus consumption, because this C2H4, which is reactant, so there's no generation, right? So the equation will become input plus 0, which is generation, equal to output plus consumption. So how can you write down like this? Input is 100, right? So 100 will be equal to what? Output, which is N1, N1 here, and plus what? Consumption. We use CONS for short. So this is equation 1. How about C2H4? So C2H4 is balances will be, because there's no input for C2H4 because this is products, right? So there's no input, so you remove input here, and then become generation equal to what? Output. There's no consumption, right? There's no consumption, so you remove this and you remove this. So that will be simply generation equal to output. So we use GEN for short of the generation equal to what? N2. Output is N2, right? N2 here. How about hydrogen? Hydrogen will be like the same as C2H4, which is output. And then output will be, generation will be 40, right? Because you generate 40 here. So 40 equal to output. Okay? So output is 40. Okay? What next? So according to equation, this is the key point in this slide. According to the equation, you understand the C2H4 generation will be equal to what? Generation of the hydrogen, right? Will be equal to the moles of the consumption of the C2H6. Because what? Because the geometric coefficient 1, 1, 1 here. So you need to write down something like this in order to solve the problem of N1 and N2. Okay, so if you don't write down something like this, only this one, then you need to understand this part first. Okay. So as we know, C2H4 generation will be 40. Hydrogen generation will be 40, as we know here. 40 equal to what? 40 here, and we got 40 here. So that will be 40 here, right? And then consumption 40. Okay, so this 40 here, and 1, and then 40 here. So if you put this number in this place, you will get N1 and N2. Okay. However, before that, you need to know, before you do the calculation, you need to know whether you can get these two numbers or not by using DOF. So how about the measure of the atomic species balance using the same if we use the same case? So again, let's write down input plus generation equal to output plus consumption plus accumulation. So as we know, the basis is 100. Flowchart, you already do a flowchart. DOF later. How do we do the calculation? Listen, now is that we don't do molecular species balance. We do atomic species balance. So how many species, atomic species in this case? There are only two. First, carbon atom. Second, hydrogen atom. So in the molecular species balance, you have three species: C2H4, C2H6, C2H4, and H2. Three species. But when you move to the case of the atomic species balance, there are only two species, right? Carbon and hydrogen. Obviously, you understand this will be easier. Why? Because carbon and hydrogen is a kind of atom. It cannot disappear unless unless nuclear reaction, because chemical reaction doesn't remove or doesn't increase the atomic species, right? So you will become very easy. There's no generation of carbon in this case. There's no consumption of carbon in this case. There's no accumulation in this case. So basically, it's very pure, easy. Input equal to output. Carbon input equal to carbon output. Hydrogen input, hydrogen atom input equal to hydrogen atom output. So how can you do that? The input is what? 100 times what? 2 moles of carbon atoms, right? Equal to what? Equal to, you have carbon 2N1, right? And then 2N2. Equation 1. So input equal to output. How about atomic hydrogen? There are 6 moles of the hydrogen atoms times 1 kilomoles, right? 100 times 6 equal to what? Output. So there are 2 times 40, right? 2 times 40 times what? 6 times N1 times what? 4 times plus 4 times N2. So you have 2 equations, 2 unknowns. Bingo, you solve the problem. Okay, so compared to molecular species balance, obviously, atomic species balance is easier when you're dealing with the problem of the chemical reaction. Why? Right? So the summary is generally, a system that involves chemical reaction may be analyzed using 3 methods. First one, molecular species balance. Approach always need using for non-reactive systems. That's what we learned before midterm exam, right? The second one, atomic species balance. And the third one, internal reaction. That's already learned this. Each approach need to lead to the same result. No matter which method you use, you get the same answer. But any one of them may be more convenient for a given calculations. So it is a good idea to become comfortable with all 3. Why? Because you will understand for the internal reaction, when you do the computation, when you do the programming, internal reaction is easier for you to do the programming. But when you want to do it quick by your hand, you use atomic species balance. That will be easier to do the calculation. But once the process involves chemical reaction together with separation, non-chemical reaction, then molecular species, you might need to use molecular species balance for this. Okay? Right. So now I'm going to show you how to do this, how to do the mass balances with using the atomic species balance. But before that, we need to understand one term called independent. It can be in the independent equation, independent species, or independent reaction. What is this? So first of all, let's take a look at the independent equations. Okay, independent equations, I'm sure you learned this in your high school. But in the algebraic equations are independent if you cannot obtain any one of them by adding or subtracting multiple of any of the others. So why is independent? For example, I give you two equations here. how many independent reactions here? Sorry, how many independent equations here? Or on the other hand, can you solve the problem of the x? Can you get the answer of the x and y using these two equations? Can you? No, you cannot. Why? Because the equation 2 is equal to equation 1 times 3. So you cannot get the answer of x and y because there's only one independent reaction. There's only one independent equation. Okay? If you have two independent equation, then you can solve the you can get the value of the x and y. But unfortunately, you only have one independent equation in this case. So number of independent equations is 1. Okay? I'll give you another example. Equation 1 is this. Equation 2 is this. Equation 3 is this. How many independent equations in this case? On the other hand, can you get the answer of x, y, and z using these three equations? It's a little bit tricky here. But when you find out the equation 3 is equal to equation 1 times 2 minus equation 2. So actually, there are only two independent equations. So unfortunately, you cannot get the answer of x, y, and z using these three equations. Okay? Right. So how about independent species? What's the case of independent species? For example, you have nitrogen, oxygen, methane, and argon. These four chemical species. And then if two molecular species are the same ratio to each other, whether they appear in the process or its ratio is incorporated with flowchart labeling, balances on those species will not be independent equation. What does this mean? For example, if you have 4 species, 5 species, and 6 species, but the nitrogen and oxygen are always in the same ratio. What does that mean? It means that you just introduce air into this process, because air is about, there are 21% oxygen, 97% nitrogen. It's always a constant ratio. It never changes. So you cannot regard oxygen and nitrogen as two species. You can only regard oxygen and nitrogen as one species, which is air. Okay? Unless it involves chemical reaction, that's another story. Because the ratio will change in the input stream and output stream because you consume oxygen or you increase oxygen in this case. Okay, so here I give you an example. So if I introduce air into this reactor or into this process, the oxygen marked as N1, which is unknown. The air of the N2, the amount of the nitrogen will be always 3.76 N1 because the ratio is 21% to 79%. Okay? And this have a carbon chloride, which is N2. So as you know that you have always the same ratio. The gas come out if this doesn't involve chemical reaction. So you have an N4, N3, and N4. And again, N nitrogen ratio will be the same as this one. Okay? And this liquid. So you have unknown 1, 2, 3, 4, 5. You don't write down this and this one as an unknown. So independent equations are what? How many equations you can get? Input equal to output. 2 species only. You don't write down 3 species. You can regard this as a 1 species only. Either you use nitrogen or either you use oxygen. Okay? Right, so if you have these 3 species into this reaction and I ask you how many independent species, what's the answer? A, 3, B, 2, A or 2, A or B? B, right? B. Right, the third one is called independent reaction. So chemical reactions are independent if the stoichiometric ratios of any one of them cannot be obtained by adding and subtracting multiples of the stoichiometric equations of the others. So for example, equation 1 is A become 2B. Equation 2 is B become 2C. B becomes C. Equation 3 reaction 1 is A become 2B. Reaction 2 is B becomes C. Reaction 3 is A become 2C. And how many dependent reactions? There are 2 only. Okay? 2 only. Right. We have 10 minutes to go. So let's finish the section 4.7c first. Molecular species balance. So molecular species balance, now let's introduce the concept of the degree of freedom analysis here. So balance on reactive species must obtain generation and consumption terms that I just showed you in the previous example. So you have input plus generation equal to output plus consumption plus accumulation. But normally we remove the terms of the accumulation. So what's the degree of freedom? Ladies and gentlemen, in your final exam, again, I want you to tell me DOF using atomic species balance and using molecular species balance. And this is what you are going to learn here. There are 4 terms here. Degree of freedom. One is unknown, which is plus sign. Second is plus sign, which is the number of the independent chemical reactions. How many chemical reactions involved in this reactor? In the previous examples, we have 4 chemical reactions. We have 3 chemical reactions. If you have 2 chemical reactions, that means what? You have 2 axes, right? You have 2 axes, external reaction, right? You have Xe1 and Xe2. If you have if you have 3 chemical reactions, you will have 3 axes, Xe1, Xe2, and Xe3. That means what? That means you have to add 3 unknowns here. Okay? And so not only 1 plus, you have 2 plus. And now, for the degree of freedom analysis, you have independent molecular species balance. How many species? It need to be independent. Independent species. Okay? If you have 3 independent species, that means you can create 3 equations. Input equal to output. Oh, no, not now. Input plus generation equal to output plus consumption, right? And then again, you have minus other equations related to unknown variables. That will be specification, right? Like selectivity or yield or something like this, right? That's specification, laws of the physical laws and physical property, physical constraints, right? You write down other equations you know. So if you have 2 plus and 2 minus, and you do a degree of freedom analysis here, and then you have number of degree of freedom. If this reach to 0, then bingo, you can get the unknowns, right? Okay, so now let's practice this using the same example. C2H6 becomes C2H4 plus oxygen. Could you please tell me how many unknowns in this case? I just told you, if you draw the flow chart, you have N1 and N2, right? So how many unknowns here in this case? You have 2 unknowns, right? And how many equations? Why, you might think, Professor, why we need to put plus in this sign? Because again, you need to know the internal reaction, which is Xc, right? Xc. So if you have 1 equation, you have 1 Xc. If you have 2 equations, you have 2 X's. So this is what? How many of this? What's the number in this case? You have only 1 equation, right? So you have 1. Okay? So how many independent molecular species balance here? How many? C2H4, C2H6, 1. C2H4, 2. H2, 3. You have 3 independent molecular species balance, right? And in this case, there is no other equations like specification, physical laws, physical constraints. That will be 0. So bingo, you know that according to DOF, you can get answer of N1 and N2 using molecular species balance. And what can you do? You just do the calculation, right? Okay. So how do you do the calculation? Input plus generation equal to output plus consumption, right? And you need to remember the stoichiometric ratio, coefficient here and ratio here. Just I introduced you in the previous slides. Okay. So here I just tell you that. Please do this by yourself. Okay. Okay. Now 4.7 atomic species balance. This is very important, and you need to learn, or you need to understand these tools, because this is important. This will show in this will show in your final exam. Okay. So atomic species balance, all balances on atomic species. So it's carbon, hydrogen, oxygen, etc., something like this. So input plus generation equal to output plus consumption and accumulation, and it become always input equal to output, because there is no nuclear reaction. So there is no generation of carbon, there is no consumption of hydrogen, and there's no accumulation, because this is a steady state process. Okay. So how can we do a degree of freedom analysis? First one, unknown labeled variables, right? And then minus independent atomic species balance. And then if there's a molecular and doesn't involve chemical reactions, so we use molecular balance on independent non-reactive species, and minus other equations related to unknown variables. So there are 4 terms: 1 plus, 3 minus, one atomic species balance, one non-molecular species balance on independent non-reactive species. And this is the same as the atomic species balance, right? So if you do this calculation and the answer tell you is 0, then you think, wow, good, I can solve the problem. I can get the unknowns. So what's the difference between this DOF and the molecular species balance? DOF for the molecular species balance. There's no number of independent chemical reactions, which you don't regard as an axis here. So save you trouble, right? But you need to add this term here, because chemical reactions might have inner gases, which can reduce the speed of the chemical reaction. Right? Right, so let's do this case again. You have plus unknowns, you have minus unknowns, minus independent atomic species balance. You have minus molecular balances on independent non-reactive species. And you have minus other equations. So could you please tell me how many unknowns here? How many atomic species balance? In the molecular species balance, there are 3 species, right? How about atomic? Only 2, right? Why? Because it's chemical atomic species balance. So you only have carbon and hydrogen. Carbon input equal to carbon output. And how many independent atomic species balance? Sorry, this is 2 here. You have 2 unknowns. Again, it's N1 and N2, right? And you have 2 independent atomic species balance. Do you have any molecular balance here? No, there's no inner gas. So this will be 0. This will be 0. So 2 minus 2 will be 0. So you have 2 equations. You can solve the 2. You can get an answer of 2 unknowns. Okay, so just give an example. Degree of freedom analysis. You can do the carbon calculation and carbon atom balances and hydrogen atom balances. So you only need 2 equations. Right. Please work with me for another 3 minutes. I will finish this soon. So internal reaction here is single reaction and multiple reaction. You all know this already. So what happened to degree of freedom analysis? There are 5 terms. First one, unknowns, again. The second one, independent reactions. Again, you want to know X1, X2, X3, something like this. The third one is independent reactive species. The fourth one is independent non-reactive species. So it's related with species. And then minus other equations related to non-variables. So if you do this, and you got an answer of 0, then you can solve the problem. Okay, so what I want to show you again, the same example. So how many unknowns here? 2, right? N1 and N2. Right? How many independent reactions? Like molecular species balance, you have 1, right? 1 independent reactions, which is this one. And how many independent reactive species? 1, 2, 3, right? You have 3. Now, how many independent non-reactive species? 0. You have other equations? No. So you will have 3 unknowns and 3 equations. So again, bingo, you can solve the problem. Again, the answer of N1 and N2. So please work out this by yourself. Okay? So let me summarize this. When you see the DOF, right, you understand atomic species balance generally lead to the most straightforward solutions procedure, because you only have 2 equations. But for the molecular species, you have 3 equations. For the internal reaction, you have 3 equations. And obviously, 2 equations is easier to get an answer quickly, right? So especially when more than one reaction is involved. So external reactions are convenient for chemical equilibrium problems, and then when equation solving softwares is to be used. So equation solving softwares is that you need to do the computation. So the molecular space is more complex calculations than either of these the 2 approaches, and it should be used only for simple systems involve one reaction. Okay, so normally atomic species balance is the first choice. Okay, right. So on Wednesday we will start to introduce this example, which involve 2 chemical reactions, and we use the 3 methods: atomic species balance, molecular species balance, and external reaction to solve this problem, to get the answer from of this example. Okay, right. So that's it for today, and I hope you enjoy the lecture today.